Welcome to our webinar. Today it's about pumps. We did one on pumps a few months ago with Chris. So you probably recognize Chris Christian. What can I tell you? Well, this one's going to be different because the last one was more theoretical. This one's going to be more practical, meaning less theory, of course. So look, I have gray hair. I'm supposed to, people think that these guys who've been in the industry forever are supposed to know everything. I mean, that's one of the secrets that young energy engineers don't understand is that the old guys don't know everything. They know a lot about some things and they don't know a lot about some other things. That's just how it is. And this pumping stuff is something that I didn't realize how weak I was at until I listened to Chris a couple months ago, and I realized, geez, I don't know a lot of things. This session he's going to talk about, or he's going to do, is going to be more, let's say, practical, and I think more accessible to folks like me who don't want to get all theoretical. I just didn't want to do it. Anyway, Chris, why don't you just introduce yourself and then we'll get going.
Okay, I am Chris Christian. I live here in Fort Worth, Texas. I work for CBRE, and my client is Christus Health. It's a regional healthcare organization, a lot of hospitals, clinics, and such as that. But I am the energy manager, energy engineer for that organization. I've been in this position for the last 2 years, but I've got 42 years of experience in test and balance, mechanical systems, controls, building automation, energy management, whatever you want. I've probably done it in this field, which is a little embarrassing, but I come to you with all this experience, and what you'll see in the presentation, I'm trying to communicate that experience as quickly as I can in an hour. But first, my purpose today is to give you an idea of what to look for when you're challenged to assess plant pumping and hydronic systems, pumps, chillers, boilers for energy management based on my 42 years of experience in a 1-hour presentation. Okay, I'm going to tell you right now, I'm not going to give you 42 years of experience and voila, you're an energy manager, engineer with all that experience. But what I'm going to tell you is I'm going to basically tickle your brain to get you to think in these terms and what I do on the job site. And so this is me, this isn't me, but this is me most of the time because when I'm challenged with the project, I've got to do a lot of searching. First is, and this is one of the first questions you need to ask, what's the purpose and the focus of the project? Are we trying to reduce energy use and cost, or are we trying to improve the overall operation of the system, or can we do both? I've had projects in the past where we were called in for energy, and it turns out that there was a problem with the way they're operating. We had a pharmaceutical that was trying to improve their water temperature. They needed colder water. So their approach was to increase the amount of chillers they had. So they were looking at installing a new chiller to tie into the existing system to get colder water. Now that is not a logical assumption. And I don't want to offend anybody out there, but more chillers does not equal colder water. Okay, so we started looking at how they were operating. We found out that they were mixing return water with the supply water, and that was warming their water up beyond the capacity of the plant, and that's where the mistake was. So we improved their performance and operation. At the same time, we also looked to reduce the energy because they were using a lot of energy to re-chill that water that they're warming up. But that's one of the first questions you're going to ask when you look at this. What is the focus of the project? Now, you need to prepare for your visit, and what tools you have in the bag matter. You need to have an inquisitive attitude. You need to want to know all the answers. Ask the questions, know the answers. You're finding facts and solutions, not fault and blame. You cannot sit there. You will die in the desert if you keep falling into that pit that whose fault is this and who's responsible for it, and we're going to chase that guy down and beat him up. Well, you can't do that. You got to be flexible in your approach to these projects. A rigid and narrow approach will give you narrow, inflexible results. You need to have solutions that apply across the board on the situation that you're dealing with. You may be looking at a specific issue, but you also have to realize that the solution may cause other problems. So you got to widen your focus to begin with. You got to see the project in its entirety. Look at the entire system, everything that it's going to touch. Then you narrow your focus to issues as you're uncovering them. and the opportunities will start appearing, just about automatic. So before you even put a step onto the site, you need to get as much information as you can prior. Know your current operational status. You got to talk to the client. Repairing failed or non-functioning equipment would be ECM number one. If they've got a lot of equipment that's broken or just not working, a ball in hand, or for whatever reason, you need to talk to them about getting that back into auto as fast as possible, because really you can't come up with a solution if everything's running in manual 100% with no real automation or control. You need to have a trend log plan to implement, but do not generate trend logs unless you're prepared to analyze them. I know that we've gone on some sites where we were logging everything, and I was standing there trying to figure out, okay, we're spending almost a day on site setting loggers, but are we going to look at these after we're done? Who's looking at these, and what are they going to generate out of them? You really got to think about your plan on what you really need to know, what you absolutely have to know, and then the rest of it is extra. But I tend to describe it as the critical few versus the trivial many. Somewhere in there, the critical few is going to point to the real problem that you're trying to solve, versus getting lost and off into the weeds with this chasing down little things. Gather as much information as you can. Plant drawings help, but sometimes you can't get them. Now, this is an example of a system, in fact, the one that I'm working on right now, where this was submitted by the vendor. And these are handy because you can look at these and it helps you to get an idea of how it's supposed to work. Plant drawings, flow diagrams, equipment layout. Remember that though, building automation control systems does not equal energy management control systems. This is a control system to control equipment to do what you tell it to do. It is not designed until you actually implement some kind of an ECM to save energy. Until you actually say this approach will save energy, it is not energy management. It is a fundamental control system. Okay, control diagrams that include sequence of operation. These will tell you whether you're an energy management project or just a plant control operation. If you see things like change the set point to this when in response to something else, then you might be into a more energy management versus control the set point to this and fixed. You know, it doesn't change at all. We're constantly going to keep the temperature the same. Does the sequence work to reduce energy use to the minimum necessary to just control to a set point? That's what divides the line between controls and energy management. Tab reports are important if you can get a hold of these. First off, it documents the entire system that you're looking at. Now, it could be incomplete, that's possible, but at least gives you somewhere to start. And it documents the system operation equipment from day one. This was how it was set up to begin with. This could be 20 years old, 10 years old, or last year. But it tells you kind of an idea of if they found any issues during that time that was going to fall short of performance. It establishes the equipment performance at the beginning of the project. And then you can compare that to now. What has changed since then? New equipment has been added. You know, they added another chiller because they want colder water. Well, no, that's going to give you more water, but it's not going to make it any colder. Or if they added new equipment that's different from the original. So when you do the site walk, you've got this in hand saying, okay, they put this pump in, but now this one's in its place and it's different. And these are examples of actual projects, okay, that I'm showing you. Commissioning reports, their operation over a varying range. So the difference between a tab report, tab sets up the system in minimum and maximum condition. Commissioning reports test everything in between. So you get to see what happened when they changed the settings and when they actually physically change the operation while they're watching it. They show you how the system reacted when the operation conditions change. They noted any deficiencies or failures under certain conditions and configurations. That's key if you're going to try the same thing on one of your ECMs, that you may change the configuration or the approach to something different, that they might have tried that at commissioning and they came up with a result that may be good or bad. I've done that before where we've improved the performance on the system where we made a minor change, but I also found out that you don't want to do this, you know, and I would note that. And that's where these comments come in. A properly commissioned system will tell you where you can operate safely and if it ever worked properly. Did this system ever work properly? It also tests the original sequence operation, compare that to the operation to present. So you could actually say it was designed or they commissioned it operating like this, and then when you get on site, it's completely different. They're operating in a completely different way. Have in your mind how to think it should operate from the data you've collected. You must start thinking in terms of, I think it ought to operate like this. Even though they designed it and put it in like that, I think it should be like this. And so kind of note that down. And in this project, I circled or I highlighted this little comment. I made this comment. Chilled water tab confirmed at being at approximately 90 GPM with all the air handlers at 100%. When the control valves modulate to reduce or bypass, the system resistance increased to near shut-off head to where actually you were deadheading or shutting off the flow of the pumps at 64 feet. So just if you went wide open, you're fine. But if once the valve started to control, it basically shut down the flow. And that was something that was in the report that they didn't, nobody reads these reports until later on when somebody like me shows up and say, well, look here, it's from the beginning. It never did work right. They actually went through a lawsuit in like 5 years and finally got it fixed, but everybody got sued. So preparing for the visit, you want to try to describe the system in the simplest terms to where you could understand it. I used to say, can you say it in one sentence? What kind of system it is? And it helps you when it's time to formulate the energy conservation measures. Different systems require different ECMs, the energy conservation measures. You cannot apply one ECM for all systems. You have to craft them specific. For example, a constant flow system versus a variable flow system. You will not use the same ECMs on those two systems, even though they're fundamentally basic. But you have to know the difference between one and the other. This is an example of a constant speed system. There's only one path to go, and this is about as simple as I can make it. Constant flow all the time on both circuits. There's no change there's no variable speed, no variable flow. But could I put this into one sentence? Sure. It's got a control valve to control the flow at the coils, and that's about it. But all the pumps are constant speed. The chiller takes all the water no matter what. There's no change in the operation. Be also ready to document your activity. These are complex systems. They can get into a lot of stuff. You want to kind of get a spreadsheet going that you can track what you do when you get on site, especially if you notice something. Log of activity keeps track of what you find. It may indicate deficiencies and potential improvements. Every deficiency is an opportunity for an improvement. Don't take it as just fix it, and if it's broke, take it and fix it to improve it. Always take the next step. Don't just, hey, it's failed, we fixed it, move on. No, you want to take and maximize the benefit out of that. I use a spreadsheet as a minimum of columns for equipment. I put the equipment in one column and the system or issue found, and then a potential problem and possible solution. So I can track as soon as I find it. This helps, especially as you get older, to say, hey, what was that thing that we were talking about while we were on site once you get back to the office? And then you have this list that you can go through and say, oh, well, that's not going to work. Or the next one, I said, yeah, that'll work. And actually, we'll do this even more. That'll actually improve the performance. I then include comments for as found condition, an as adjusted command. If I made it change in the setting and see what the result was and the response, and as we left it, okay, that is also key. Because if you find it set for this, you adjusted it for something else, it either worked better or worse, where did you leave that? Did you put it back like it was, or did you leave it operate as you adjusted it? That documents where your ideas are coming from and where they're going, all right? Document your questions from the review of what you're given. If you go over the system, These are screenshots of control systems on these plants. And you may notice some issues that you want to know more about. So you would also put that in as, hey, the chilled water differential temperature is too low. I want to know why. Prepare a log of activity, keeps track of what you want to know and find and indicate potential improvements or deficiencies. Set points, temperatures, temperature differences, variable speed. What speed are they operating at? We'll talk a little bit more about that in a minute. Minimum of columns equipment usage, issue found, potential problem, possible solution. You're always thinking of a solution. Every time you find a problem, you should immediately start thinking of how you're going to fix that. Okay? What if you can't get any of this information? You might be able to get some, but not all. Well, that makes it harder. You're going to have to really work harder. Simply, I take a computer or pad along with me and I'll sketch out the system freehand or on the computer. Take photos of nameplates, screenshots of control systems, something that you can bring back with you once you get on site, or if you can ask them to send them to you. Interview the staff, find out how the system's currently operating. Have they changed from the original operation and why? That's always the question, why. Develop your own idea of how the system should operate and compare it to how it is operating. Okay? And I know that if you take a picture of a nameplate on a pump, you get great information. So in this case, this pump has your horsepower, the feet, the GPM, clearly identified. If you wanted to get a pump curve, this is where you'd find that information. You could send it back to manufacturer, or even I got a pump curve from the vendor, the people who sold the pump to the job, and they were going to pull that curve and send it to me. So this thing is a wealth of information. What I want to get out of this, though, you look at that feet, it says 55, you convert that to PSI. That's something you've got to watch for when you get on site, is are they operating, or have they made the settings above that number? Because it'll never accomplish that at that flow. You want to see numbers below that actually show that you can work within what this pump is designed for. Now you also get nameplates that look like this. Same manufacturer, I think it's even on the same job, but they deteriorate after a time. They're not great, they're not real good, and sometimes they're just almost impossible to read. So you got to be prepared for what you can do to handle those issues. That one, these are all in the same job. If you notice the little yellow stripe, they're all off the same project. So they're all in different phases of deterioration. So by the time you get on site, your brain is probably going a mile a minute and say, okay, I'm pretty intimidated about what I'm going to do here, but I got to watch out. It's your first time in the plant. You're visiting somebody else. You need to organize, familiarize, take your time to get familiar with its laying out. I know that if I look at a print or a diagram, I got it in my mind, okay, it's supposed to look like this, but when I get on site, it's completely different. So you got to start matching up. Okay, I saw this on the drawing, and here it is in the plant. Organize to answer your questions. That's the key, because if you don't really know where everything is and how its relation to each other is, you don't have a foundation to start asking questions. Note that equipment is running and what is not, and why. If they've got it in. I actually went into a project on a major key site that the drive had failed. They put it in hand and they couldn't figure out why they couldn't cool the building. Well, it was running 100%. And I asked them, well, why aren't you trying to fix this? I said, well, we just haven't done it yet. I said, well, I'm going to tell you that that's probably why you can't cool this building, is because this is not working. It's in bypass. Note that what equipment is running and not. Notice the noises that don't seem right. You're going to hear a lot of noise in a plant. And your first time there, is this normal? Is this right? Is this working like it should? Gurgling, revving, constant up and down, something that's oscillating, or it's like, why is that doing that? Everything should be constant and smooth, okay? If you notice anything that changes from 1 minute to the next, note that, or at least try to find out what is going on with this. This thing is running all over the place. Surges indicate extremes, like pumps struggling to work or starving for water. Gurgling indicates air in the system. It'll sound like there's a dragon sitting there trying to swallow something. It'll go smooth and then a big gulp, and then it'll go smooth and then a big gulp. That means you've got something interrupting the flow. Alternating surges, gurgling, systems are not full, they're not fully charged. There's something interfering with your ability to move water. Pipes bleeping or hammering indicates slugs of water being pumped. They'll bang around in there, and it's like, well, is that right? That can't be right, because if it was full of water and pumping smoothly, I shouldn't notice things like that. But if you start noticing hammering or noises, just draw your attention to it. There's a reason. There's something's not right. Equipment starting and stopping, comes on and shuts off, ramping up or down rapidly. You can pretty much hear a heavy pump pulling in and starting and running up to speed, and then it backs off, and then it speeds back up. The current operating point. This is something I notice on pumps, chillers, and boilers. Where is it operating? If you have good gauges, you can look at them, and you're going to assume that they're accurate. Don't assume that all the time. But if you notice that on one side of the pump, it's in the negative gauge, 0, or pegged at 0, there's probably, it's starving. It could be starving. There could be an issue with strainers or some restriction in the water getting to the pump, or an unfull system. I had a system that passed its tab that had the correct pressure differential across the pump for design, but the system was not full. It was pulling a vacuum. But the tech who was doing the testing said, oh, I got my numbers. I said, yeah, this is the only place you've got the numbers. The rest of them, you can't even start a chiller because you don't have enough water. And the flow meters are jumping all over the place on the system because it can't get a full stream of water. We're not full. We have air in the system. And you also notice the gauges are bouncing around. You notice that indicates hammering. That's gulps of air. It's not a full system. It's not smooth. Fully loaded, full speed, low or high fire, and staying there for long periods of time, all indicate that something's just not right, that they're constantly running at a full speed. Most systems, it is rare that a system is in operation at 100% of capacity for long periods of time. Typically, and I'm talking from the very hot state, typically we only hit design conditions 10% of the time. 100% load 10% of the time. The rest of the time we're having to operate somewhere less than 100%. So be aware of that. Always wonder, why are we running at such a high level? And also be aware of policy diversity in design. I promised John I wasn't going to use these technical terms, but diversity basically says that since we rarely run at 100% load, we could probably get away with designing to 80% design. And that's happened in the past. And if you don't realize that's what's going on, you'll run into that when you're expecting, okay, I need this many tons or this much GPM, but we're not sized for that. Well, diversity allows for that because the load moves in the building. It's not going to stay at 100% all over the building. So there's a possibility that that load will shift from one time of the building to another. And so they designed to manage that by going to a certain level in diversity. But note that you'll see that sometimes. It was a trend. I don't know if it still is a trend, but it still affects what you're looking at. You're expecting a 100% design, but you see something designed for 80%. But that can happen. Look for contradictions in operation. Variable speed, variable flow, not varying speed or flow. Pumps running at full speed, but not pulling full load, amperage, or horsepower. These drives are wonderful things because you can actually look at them and see. I'm running at 90% of the speed, and I'm only pulling 50% of the amperage or horsepower. Is that okay? Am I able to operate at that point? You've got to ask yourself, okay, this is nice, but it doesn't really give me a whole lot of room to work if I'm running at 100% all the time. I don't have a lot of flexibility. I can't really vary from this. And if I do, is it going to hurt? Systems that are heating and cooling at the same time. That's one of the biggest things that I look for. I do not want to be heating and cooling at the same time. But that's a contradiction, isn't it? I'm heating somewhere that's possible, and I'm cooling it back down. That just eats up energy. Always ask why. Why are we operating at this point? I use the demonstration here. It's the kind of an unbalanced seesaw. It's obvious that we're doing something here, but it's not required over there. Comparing the full speed, this is the example I give. It's 95% of the speed, 11.9 amps, but the amperage on the motor is quite a bit higher than that. So you have plenty of room in the motor, but it's not fully operated. At full speed, it's not fully loaded. These are things that kind of indicate that what's going on. Remember, if you remember, and those of you who were on the pump webinar, you can shut off the flow to a pump and it's still going to pull amperage, even at full speed, but it's not going to be anywhere close to full load amperage. It's not moving any water down the pipe. It's not overcoming any resistance. It only does that. It only loads up. It only brings up amperage and horsepower when it's moving water. So that would indicate that it's probably a restriction. Either it's starving or somebody's got too much restriction on the discharge side and restricting the flow. So that's kind of a thing that says, okay, why? Why are we operating at full speed? And why aren't we moving enough the maximum amount of water? Contradictions, it's just manual operation where they're running in hand or overridden at a fixed set point. Why? Are you compensating for broken or disabled equipment? It is possible that they're just running in hand because they had to do that and somebody forgot about it. The alarms in the system that never clear, they're constantly in alarm for whatever reason. Do the temperatures at different parts of the system make sense? No temperature differences. If you've got cold water coming out of the plant, going out to the building and coming back, you should have warmer water. But if you have cold, like let's say 45-degree water at the chiller and 42-degree water going out to the building, that doesn't make sense. Somewhere in between, it's pulled out 3 degrees of temperature. But you're controlling the system based on those numbers. And so while it looks odd, it has a deeper meaning that's going to affect something else, because control systems look to those values to make decisions. And if you're an automatic, it's going to look at it and think, well, okay, I need to control to this, but is that right? Is that accurate? Note the temperature differences. Low deltas indicate an unbalanced capacity to load. You're overpumping the system. But again, it looks at a contradiction that I'm not getting the water to where I need to get it. That's all an issue that you're going to have to look into to resolve. The alarms are key. Points of equipment in the control system, they're overridden, bypassed, in alarm. They point to serious failings in the system and possible opportunities for savings, but you have to address these. Include the solutions to these alarms as part of the project. You want to clear these things off if you can, or at least it gives you an indication that something's not working correctly. And your ECMs, your solutions, could address and resolve these issues. Contradictions in operation. You're running 40-degree chilled water on a 30-degree day. Why? Why are you doing that? Is there any reason to do that? Why are you running 180-degree heating water on a 100-degree day? You're heating and cooling at the same time. Manual operation. Units operating in hand are overridden at a fixed set point. Why? Ask the Moneyball question. For those of you who aren't familiar with Moneyball, it was a book written that basically is an approach to baseball, where they were trying to figure out, why are we paying money for players who are supposed to be great players but aren't playing great? So the Moneyball question is, if he's such a great player, why doesn't he play great? Well, the Moneyball question, when it applies to these systems, if the system is supposed to vary speed and flow, why doesn't it vary speed and flow? If you're looking at a system that looks like it's always running at the same level all the time, no matter what time of day, no matter what time of the year, that's an opportunity for something to change. But that's again, why is it operating this way?
if it doesn't have to. Check the operation of the system through the building automation system. Look for contradictions of operation again. Has the system ever worked correctly? Can somebody prove that? That's where the tab and commissioning reports are gold in identifying problems from the outset. If I hadn't read that tab report on that project and nobody else did, I wouldn't know. And the building was still being finished when I read that. Nobody would know that that was a problem. They would just go on their merry way, but then start complaining when they couldn't cool or heat the building in certain times of the year because it could not achieve its design flow at any time other than at 100%. The staff should be able to explain deviations from the original operation as responding to complaints. Remember this, if they don't have a problem, you would not have been called in. If everything's working fine, there's no complaints, then why are you there? Are you just there to look at something that's working perfectly? No, they have a problem. And that's part of your job, is to look into that to find where the problem exists. You're there for a reason. I have a secret, okay? This is controversial and it's been actually put in print, but this has been my experience. Most energy conservation measures are defeated within the first 3 years of implementation. Complaints from the occupants drive a response from the operator. They're trying to solve the problem on their own because somebody's complaining about it. One of the first questions asked by operators during training is, how do I override the system if I have to? That is every job I've ever been on. When I was doing controls, when I was doing energy management, and they're looking into a new system, how do I override it? They want to know how to do that. And there's no such thing as a temporary override. If they find a solution outside the operating parameter, it's going to stay in. They'll find a way to keep that in. They'll put it in override through the building automation, or they'll put it in hand, or they'll manually position the flow, the pump, the drive to where it constantly runs at that no matter what. What started out as energy management becomes pain management. They want the phone to stop ringing. They want to put that aside. Please make this go away. And it's from day to day. I mean, there are a lot of people get angry. They don't like the way the system works. And especially if people looking at the money and how much it costs to put this in and it doesn't work, then it really gets ugly. And so that's part of your solution also, is to make somebody happy. I always keep a list, a master list of energy conservation measures as I go through these projects, that if I find something that works and saves energy, I note it down. What was the condition? What kind of system it operates or would apply to? And I keep this master list and how I can both implement and then measure and verify that ECM. Because that's something that you're going to end up having to do also. If you came up with an ECM on a system, pumping, that we can actually change the set point of pressure differential and the speed on the pump to make it work more efficiently, rather than you having to install a new chiller to get colder water. Okay, that's an ECM, that's an energy conservation measure that you can implement. But I note that as I go through these systems, if I didn't already do it, it's a new thing that we've discovered that we can do. I describe the system, I describe the ECM, I put in there some idea of how it was implemented and how you know it's going to work, what you look for success, and then how you're going to verify that success. You can use the IPMVP, that's fundamental. But if you come up with another way, if you did logging before you implemented and then logging afterwards, you can say you have to log the operation of this pump over a certain amount of time and then implement the ECM and then log it again after you've done that. And the difference is showing that you've improved the situation, improved the performance, reduced the energy, whatever you want, whatever your goal was in that ECM. But you have it noted here that how we prove that performance, and keep that everywhere you go, because then you don't have to keep reinventing the wheel. Now, we want to be creative, okay? But one of the keys that you need to really
focus on is that you're going to match your capacity to your load. That's the most efficient operation. Use the minimum amount of energy to accomplish whatever you're trying to do. You find the most efficient point of operation across the system's range of operation. How much GPM can I pump and still keep the equipment online? That's a combination of, will the pump work at that point, and will the chiller accept that on that case, or the boiler, or whatever it's providing the water to? Can I operate in that range? You can take multiple steps. There's multiple things you can do, and that's kind of what the illustration says. I got one big ball on one side and 3 small ones on the other, but it balances out, where I'm matching capacity to load by implementing this balancing act. Any single change can have multiple results. It can work the other way also. You make a small change here, it chain reactions through the system, and you may not know what's going on. That's where that log, where you keep track of what you make changes, that's where that log comes in handy, because if I make a change here and it has an effect, negative or positive, on something else, that's what I keep track of, whether I can continue to do this or not. But it also may lead to more of an investigation to find out why I can't do it because it affects something else. A change in chilled water temperature can save energy at the chiller, but it may cause the chilled water flow to increase to maintain the air temperature set point and the cooling requirement. So I've changed energy used at the chiller for energy I'm now having to use at the pump. Is it the same? Can I actually get away with this? But that's something you have to keep track of. If I make a change here, how does it affect somewhere else? Rarely does a single correction or adjustment solve the problem. That's very rare. In fact, I don't think I can find anywhere that I just made one change and it fixed everything. Be open to possibilities based on your experience and intuition. Intuition comes into play because it's basically your experience or your understanding that automatically kicks in and says, you know, I can do this. It's not the same as assumption. Do not equate intuition with assumption. Assumption is coming to a conclusion without all the facts. You assume that it's going to do this, that if I turn the pump on, it's going to run at the right speed. That's an assumption. No, I look at how the system performs. That's intuition that says we're not working correctly. That's where your intuition and experience come in. So I'm going to give you an example of ECMs that are derived out of looking at a project, okay? So this is a chiller. This is the performance of a chiller over certain flow rate, or fixed flow rate, sorry. And this is what you'll probably see on most of your projects. If you go this deep into a project, you're trying to find the most efficient point of operation. And in this case, this chiller seems to operate most of the time in this range of load, but the number of unoccupied hours falls down into this range of percent load. The highest efficiency, though, for this machine falls into here. So it doesn't fall into either one of the operating ranges. Most of the time, it's going to operate at a less efficient point. The unoccupied hours, it's operating down here on the bottom. Now, if you didn't know it, at the low end, some chillers are not as efficient. You want to find the most efficient point for this system to operate and try to channel that into operating at that point. Note the delta T with a constant flow of 6 degrees at the most efficient point of operation. That's the lowest energy point. 70% of the time, though, is not running in the most efficient range. So here's an ECM. I mean, you've got to find a way to get this machine to operate in its most efficient range. But what I'm going to tell you is that this is one of 4 chillers. Okay, so but we looked at this across all 4. So potential ECMs. Variable speed, variable flow will benefit this application. Remember, the minimum flow requirements keep a chiller online at low flow. Plus, you don't want to operate on that low end a lot of the time. Variable flow will improve the temperature difference across the chiller and plant. Now, I notice that this chart stays at fixed flow. This is where your experience with affinity laws comes in. You start varying the flow to match your load again, is going to change the profile of this machine. It will probably become more efficient because it doesn't have to work as hard when you're pumping 900 gallons a minute through it. When you can cut that in half to 450, it's not going to work as hard to try to accomplish your temperature difference. The plant sequencing of chillers to operate in this sweet spot of the lowest kilowatt per ton operation and match the plant capacity to the required load. You're trying to match your energy expended to the load required. Load up to 60%. If the load increases, add the next chiller in sequence to drop the, it's not going to drop the load, it's going to drop your capacity per machine, but the total capacity matches your load. But now we're operating in a more efficient point. Reduce the number of chillers when the load drops below 30%, critical for unoccupied operation. You know, we had all those hours of unoccupied that it was working at a very low efficiency point. But if I don't have to run 2 chillers, go to 1. Make it pick up the load. Maybe you can get it up to 50%, the most efficient point, rather than running 2 chillers at 25%. Maintain the same flow rates through each chiller to maintain balance. That's where your variable speed is going to come in. You'll probably have to add something that will tell you what the flow is, like a flow meter or pressure differential, and do the calculation. Just something that will tell you what the flow looks like going through each machine, so you can actually make a decision and vary the speed automatically through each machine. You basically have, instead of 900 gallons per minute going through one machine, 450 gallons going through 2 at the same time. But that will make it operate at the most efficient point. Try to maintain that balance. So, concluding this presentation, you're an investigator looking for answers, just like Sherlock Holmes. You're going to use every tool in your bag, from deduction, inspiration, intuition, and very little assumption. Do not assume anything that is working correctly. You've got to verify. Don't be afraid to experiment and innovate. There's a mantra that we had in commissioning. If it's not broke, break it. And the people who were engineers and such as that were kind of afraid of what that really meant. Well, it meant that you're going to push it. You're going to push it to the limits to find out where you can operate. Because if you don't know, you have to find out. There's got to be a way for you to know how far you can go and where you can't go past that point. But that's the only way to do that. If nobody can tell you, if you didn't have the information to begin with, like a tab report, commissioning report is supposed to push it to the limit. Tab report is supposed to give you the minimum, maximum operating points in the system. If you didn't have that, you're going to have to find out for yourself. Get and stay organized, and the results will appear. It's almost like magic. Once you get it down to the point that you understand what's going on, it kicks into your brain that you're actually going to come up with a solution, because you can think about all the things that are possible and then narrow that down to all the things that we can do. But the only way to do that is to get this information organized and kind of tickle your brain to get these ideas coming forward. And like I said, this is from my experience. Your experience would probably be different. Make it your own. That's the key also. I should put that in there. Make these projects your own. Be a part of that solution and be involved in it. So that's my presentation.
So I've got a question. So can you go back a slide? So this one confuses me, because first off, where did you get this kilowatt per ton at all these different loadings? Did you calculate it with curves you got from somewhere, or did you actually measure the flow rate and the delta T and all that stuff and calculate it yourself?
A lot of this chart came from the manufacturer.
Okay.
This was their submitted level. Okay, they may have done it in 10% increments, and then I added the 75%, the 25%. And typically they might give you a 10, 20, 30. But I when I got to the site, I started seeing it operating in those in-between zones and trying to figure out, okay, is this the most efficient point? No. And then so I find out that no, it's not. If I started another machine and cut the flow will it dial me into the more efficient point of operation? And it did. And in this case, I can prove it on a project that we did this.
Okay.
Cut the energy significantly.
Oh yeah. So a couple of things. So one is, I think your basic orientation or approach is something that unfortunately a lot of at least ESCO engineers do not do, because I guess maybe they're not given the freedom to do it, and maybe they don't have the time when they're on site, which is to sit at the control system and, as you say, push it, see if we can break it, or maybe not see if we can break it, but see what happens if we do this. Now let's look.
Yeah.
And that, unfortunately, I mean, that kind of tweaking, that to me, that is like, I mean, I have a little bit, you are a geek, and I have a little bit of geek in me, and that seems like that is so ideal. It'd be like going to Disneyland as a child, to be able to have a central plant and be able to screw around like that and see how these different inputs or changes will affect everything else. And then you can see if you really save something. That is the approach. I really like it. Back to this though, I question this, and that's because I don't know, and that's why I'm questioning. And that is, when you got this curve from the manufacturer, is this a water cooled or air cooled chiller that you're talking about here?
This is water cooled.
And then did you assume, or no, did they assume the same condenser water temperature going into the chiller, or did they assume different condenser water temperatures at different loads?
They did not assume, they assumed a constant temperature. That assumes that, okay, here we go, we're talking the wrong word. They assume that that's what you're going to operate. There will be 85, 95, 78, the typical arrangement for condenser water.
So the question, so I had a couple questions. So one is, and you or other people have heard me say this before, like, the people, a lot of us engineers, we went to school, we got really good at math and computer modeling and all that crap. And we end up using these curves, like these DO2 chiller curves, which assume at 100% load, it's really, let's see, how's that work? It's really hot outside, and at 50% load, it's a lot cooler outside. Right. Therefore, the condenser water temperature is different at different loadings. And so the curves we're getting at a DO2 or trace or whatever are crap. And we end up, recommending staging sequences that don't make any sense, because they're based on, what we really needed was, we needed a constant condenser water temperature coming in, so then we could really evaluate, I guess you can say, compare apples to apples when you're looking at, the different loads of a chiller. But that aside, the question I have is on the delta T column, because the general, I guess you can call it assumption, which is, you're right, our assumptions are often wrong when we walk into these mechanical rooms. But the delta T, where you're saying this chiller is doing the best, is really low. In fact, you're saying even a 2 or 3 degree delta T is really good. Whereas, the conventional wisdom is, no, you want a 10 degree delta T or a 12 degree delta T. Yeah. That's what we want. Otherwise, we're going to have these real problems with the chiller. Can you discuss that?
But that's why I'm using this as an example. What is wrong with this assumption is that it's a constant flow rate. That's where we're pointing to an ECM. That's where your ECM is to vary the flow to improve the delta T. That's where, and I know, John, you've asked me this question before, is it better to run 2 pumps at 50% or 1 pump at 100%? In this case, it's better to start another machine to get a better performance at a lower level and improve your delta T, because now I'm going to start a second machine and a second pump running at 50% to get into that sweet spot on this chiller. I've got to do something to get this dialed into where that chiller is most efficient and improve the delta T. So the only way I can do that, the only way, is to vary that flow to get the delta T different. I slow the water down going through the machine. It has an easier time getting 10 degrees across it.
That's right.
So then I get it dialed into this lowest kW per ton. I'm going to say, and I've proven this, I think, that it is a lower kW per ton at lower flow, but a better delta T.
both of which are great.
And that's the kW per ton is just for the machine, the chiller itself. You're also
Right.
going to have to add the energy you use in those pumps, and those running at 50%. If you believe the horsepower is like, you know, the square root of 3, that goes down to that level that you're pumping a lot less water. The pumps have an easier time pumping lower flow than 100% flow.
Yeah, so that, and what it means is that this chart itself becomes moot very quickly as soon as
Quickly, it gives you an idea. Yeah, but they all look like this. They're all at constant flow rates.
Yep.
They don't look at the ECM potential of maintaining a constant delta T. Keep a constant delta T, you're going to run the most efficient on the chiller. It just automatically dials in to maintain that delta T where your flow falls in. And I want to get that below 50% of the capacity until I have, in this case, 4 machines. If I get all 4 machines running and the load keeps going up, then all 4 machines keep going up. That's the best I can do, no matter what. But I'm still running at the lowest kilowatt per ton per machine.
Yep. I know. Gosh. Okay. So this is probably asking what I asked in different words, or something similar, I guess. Here's a question from someone, and that is this chart saying that the existing condition is constant flow? It's 900 GPM across the board at the full range of loading. Yeah. Why would you want to run max flow rate at 20% load?
But this is right out of the manufacturer. That's right off their cut sheet for the project. And that's why I don't see them. It's rare that I see a variable flow performance on a chiller. I have to do that myself. So yeah, that's where your affinity laws come in, and then you have to verify in the field. If you have the ability to change the flow through the machine, then you can now put a kW meter on there and actually calculate your performance kW at different flow rates. That's what you're going to end up doing. That's how you verify the performance on this ECM.
Yeah, it becomes very complicated because of all the different flow rates, et cetera. And then you end up with a different chart for each flow rate, all of that. And it makes you, and it doesn't make sense, like Charlie said here, to have just the same flow rate in a chart like this.
Yep.
And so
no, but that's what we get.
It almost makes that's fine, but it almost makes the case for that's why AI actually might end up being really, really good at this, because it's tested it at all these different things and remembered all the different settings, and it's just going to say, yeah, this cow can run. Because I would think if I was doing a job like I imagine you do, I would I'd try something, see how, and I'd calculate kilowatts per ton or of the plant, and try it again, kilowatts per ton of the plant. Granted, that may affect the air handler hands as well, but let's pretend they aren't important. And
that's
I come up with one answer. It's not like it's not like there's a parabolic type, answer where it's, oh, here's the optimum point. I think it's probably kind of just, there's all these different points, all these local maximums all over the place, and that it's beyond what a person really could understand, and it ends up being an AI issue.
Well, no, I want to say no to that, because we know the parameters. That's why one of the things you're supposed to do is to kind of set the limits on where you can or can't operate, and know that going in, that you can't go beyond this point. But everything in between is fair game. That you have the opportunity to make a change and improvement. And if you came up with this as an idea that why can't we do this? That's one of those things that you're sitting there, you're looking at the system operate and say, why can't we do it different? Why can't we improve this? Is there a reason why? And you mentioned that I've actually worked on projects where they only allowed certain ECMs. It would not allow you to deviate at all from the list they had already approved. This is what we're going to do. And it's like, well, there's an obvious solution sitting here right in front of me, but we're not going to do that because it's not on the list. And it's like, my gosh, get away from that. I can't express that.
Everyone, thanks for coming. Chris, thank you. That was really good. I really enjoyed it. And I'll see you all here. Goodbye. Thank you, everyone.